back. And our next speaker is Professor David Xianfeng from Stony Brook University, who will talk about geometric understanding of deep learning. Welcome.
Okay, thank you. Thank you for the invitation. So today I'm going to report our recent research using geometry to understand deep learning. So this is a collaborative work with Professor Xianfeng, Professor Luo, and Professor Wang, and many mathematicians and computer scientists. Okay, so more than 30 years ago, okay, almost 31 years ago, Professor Yao raised this open problem. Basically, there was a very famous open question in convex geometry. How can we determine the shape from curvature? Okay, it's called a Minkowski problem. Suppose we have a convex surface, then we define Gaussian curvature. Using Gauss map, we can carry the Gaussian curvature to the unit sphere. And given this spherical function, how can we determine the shape? And Professor Yao raised this problem in 1993. In order to solve this problem, we developed some computational method based on geometric analysis. And after 30 years, okay, it turns out that this is the foundation for generative AI. Okay, so today I'm focused on this aspect. So here I give you one example to explain what's the meaning. Suppose we have a cortical surface, okay, reconstructed from CT image. Then we normalize the total area equal to 4 pi. We're using conformal map, map the cortical surface to the unit sphere. So this conformal mapping will push forward the area element from the cortical surface to the unit sphere. So therefore, on the unit sphere, we have a measure, okay? So that measure is induced by this mapping. Then we treat that measure as a Gaussian curvature for some shape. Can we determine that shape, basically? So that's the convex shape. So the Gaussian curvature of this shape, okay, carried by Gauss map to the unit sphere, okay, and equal to the given measure. So basically, so here we can see another example. This is a Max Planck statute, okay? We conformally map the surface to the unit sphere. We normalize the total area of the surface equal to 4 pi. Okay, so this mapping push forward the surface area element to the unit sphere. So on the unit sphere, we define this kind of measure. We try to find a convex surface whose Gaussian curvature measure equal to this measure. Okay, and using our geometric analysis method, we can recover such kind of surface. Okay, then the method is based on something called optimal transport. On the sphere, how can we calculate optimal transport? And the optimal transport today is the foundation for AI. Okay, so that means mathematics is really useful, right? You invented something 30 years ago, and after 30 years, AI develops. So here we show another related problem. Basically, suppose we have a flashlight, and how can you design the mirror surface, okay, such that when you turn on a flashlight on the wall, you get this kind of image. So basically, how can we convert the point light, okay, to lighting energy distribution? Okay, so that's the problem. So basically, by solving the spherical optimal transport, which is a Monge-Ampère equation, we can design such kind of mirror surface. Then if you put a light source, the reflection will give you this kind of distribution on the wall. Okay, so this is very useful for antenna design, okay, in the optical field. So here we show another example. This is the Monge portrait. Now how can we design a mirror surface such that the reflection density is equal to the given density? So that's the mirror surface. Then we can change from mirror surface to lens. How can we define a lens such that the refraction from point light source, okay, give you this kind of lighting energy distribution? So basically, how can we convert one distribution to another distribution in the most economic way? That is the optimal transport, and reduce to Monge-Ampère equation. Okay. Okay. Now we know that AIGC is really hot, right? So the meaning for genetic model, meaning we use a computer to generate a random noise. So like this picture. So every pixel is a random number using a pseudo number method. Okay, then you generate this random image. Then you put into the genetic model. The output is a human face. So basically, we will see this method is really popular today, but the foundation is still motion P equation. Okay, and we can using this geometry mu to explain the fundamental principles behind deep learning. So people has invented many models based on that. The GAN model, bidirectional autoencoder model, flow-based method, and diffusion model like Sora. Sora extremely hot these years, right? Okay, everything is based on the same mathematical principle, but different technical details. And there are a lot of mistakes, a lot of paradox for today's AI model. Then we can explain why that happens and how to improve. Okay. So basically, we try to answer the following three fundamental questions. So what does a deep learning system really learn? So deep learning means we try to learn something, right? Now what's the target we try to learn? How can we mathematically describe the learning goal? The second one, how does a DL system really learn? We know the neural network has so many neurons, right? So billions. So therefore, the capacity is huge. So in principle, the network can really memorize everything. Now how can you justify we really learn something or just memorize? Okay, from a mathematical point of view. Then how well does a DL system learn? Does it really learn everything or have to forget something? What's the fundamental reason for that? Okay, basically. So the first one, basically, we call something manifold distribution principle. So basically, given a natural training data set, okay, we can treat it as a probability distribution defined on a low-dimensional manifold. And this low-dimensional manifold is embedded in a very high-dimensional ambient space. Okay, so here I give you one example. So this is Xianfeng's amnist data set. So he collected every image from envelope, from post office. So therefore, each data set, each training data is a image, 28 by 28. So we treat each image as one point. Okay, the dimension is 784. So therefore, a training data set is a point cloud. Okay, so the dimension for every data is very high, but the dimension for the point cloud is really low. So that's the tricky part. Okay, so if we treat every small image as one point, so the dimension for the point is 784. So we get a dense point set. Okay, but we can flatten the point cloud to the 2D plane using t-SNE method, Hinton's t-SNE, right? And this mapping is one-to-one, okay, and it's a homeomorphism locally. So this means that although the dimension for data is really high, but the manifold dimension is really low, okay? Now here we have 10 digits, okay, from 0 to 9, and each digit is actually corresponding to one cluster on the 2D plane. So therefore, every digit basically representing one distribution on the manifold, on the latent space. So therefore, in general, we can treat the training data set as a low-dimensional manifold embedded in a very high-dimensional ambient space and corresponding to different distributions. Okay, so that's the goal for deep learning. So basically, so people has invented many methods for this kind of manifold embedding. The t-SNE method very famous. Okay, okay, 7 is embedding. You can see the latent code for every image here. So this one using UMAP. So if you read the construction method for UMAP, actually it's a mimic witness proof for manifold embedding. Same thing, just one is a computer realization. So here we embed the amnist to the 2D plane. Then we get 100 samples. So each point here is one sample. Then from sample, we decode, we get the original image. So you'll see that, so if the sample is inside, the support for the distribution, we get a very precise image, very sharp image. But if you get a sample, on the gap, in the gap between different clusters, we get a very obscured, reconstruction result. So this means that precise information for the distribution is very important. So when we try to generate, we shouldn't go beyond the boundary of the support. Okay, and this is really hard. Okay, so if you see some generated model or image is very blurred, so that means the sampling on the latent space is not on the support. Okay, Okay, so everybody knows manifold. So basically, we have image space, very high dimension. In this space, we have this data manifold of a very low dimension. And we get one open side. Okay, then we're using a homeomorphism map to the latent space. So this mapping is called encoder. So the inverse is called a decoder. Okay, and you can choose different encoder. Okay, they differ by this transition map. So basically, it's a manifold definition, right? Okay, so here we can visualize the concept using a low-dimensional example. We have a 2D surface. So the dimension for the surface is a 2D, but every point on the surface is a 3D. So you'll see the difference, ambient space and the manifold itself. And we flatten the surface to the 2D plane using Riemann mapping. This is called encoding. Okay, the inverse is called decoding. Okay, so encoding is a homeomorphism, basically. But then there are many, many different ways for encoding. If we're using this encoding, so if we put uniform distribution sampling on the latent space, so when we put back, we get a highly non-uniform distribution. So you'll see that the forehead part is really sparse, so that the belly part is really dense. So this means that this kind of embedding or this kind of encoding destroys the original distribution. So this is a bad example. But if we change to this encoding, we uniformly sampling on the latent space, we get a uniform sampling on the 2D manifold. So therefore, in this case, we reduce the dimension, but also we preserve the distribution. So that's the ideal for deep learning. Okay. So in summary, the central task for deep learning, there are two. The first one, we try to learn the manifold structure. And the manifold structure is represented by encoder-decoder, which are two neural networks. So neural network can do only one thing, the mapping from one Euclidean domain to another Euclidean domain. So therefore, all the information is encoded by neural network, which are the mapping. This mapping gives you the topology, okay, for manifold structure. The second part is learning the probability distribution. And this one actually is learned by optimal transport. So computer can only generate a uniform distribution. So therefore, you need to find a transformation from uniform distribution to data distribution. Okay, all the information is encoded by this step. Okay. So here we see a typical genetic model. You have training data set, and you train the encoder, encode everything to the latent space. Then you train the decoder from latent space, it goes to the data manifold. Okay. Then you're using computer to generate uniform distribution. And you find the transport map from this distribution to this distribution. And currently, people using diffusion model a lot. But then later we will see the diffusion model actually has a lot of shortcomings. Okay. Then we propose to use optimal transport. Okay. So therefore, this arrow is a neural network, and a neural network, basically. So if we try to generate human facial image, same thing. So each facial image is treated as one data point. Then the training data set is treated as a low-dimensional manifold. And the different gender, different biological feature can be treated as different distribution densities. Okay. Okay. Using this point of view, we can reformulate a lot of classical problems for image processing. For example, if we try to do the noise, given noisy image, how can we recover the original very sharp image? So using conventional method, we will using a Fourier analysis, right? We do Fourier transformation and we remove the high frequency part. Then we're using low pass filter. Then we do inverse Fourier transform. But for deep learning, basically we're using geometric point. So basically we're using clean facial image to train this data manifold. Then suppose we have a noisy image for human face. Then it's a point very close to this manifold. Then we do projection. We find the closest point on the manifold to this point. Then this gives you the clean image. So therefore, image denoising is a geometric projection. Okay. So this method actually gives a much better result comparing to conventional method. But this method heavily depends on the data set. Okay. So suppose if we're using the cat face. So here we use a cat face to train manifold. Then we do projection. The recovered image is a combination between human face and cat face. Okay, so therefore, the deep learning method actually has a lot of prior knowledge encoded by this data manifold and encoder, decoder, and distribution. So therefore, it gives you a lot of background knowledge already. So for image processing, give you much better result. But heavily depends on the category. So if you change the data category, you have to change the manifold. So that's the key difference. Okay. Okay. For optimal transport, so basically here we do brief review. So given a manifold with a remaining metric, then we consider all the probability distributions on this manifold. Okay, then all the distributions form an infinite dimensional manifold, which is called a Wasserstein space. So deep learning basically try to do optimization in this Wasserstein space. So therefore, we have to define. So for example, for conventional maximum entropy principle, okay, maximum likelihood estimation, maximum posterior estimation. So all of them basically is doing variation, optimization in this space. So therefore, we need to define absolute derivative in this space, okay, or covariant calculus. So therefore, optimal transport give you such kind of theoretic framework. So basically, optimal transport define remaining metric for this Wasserstein space. From this, remaining metric, you can define Levi-Civita connection. You can do a lot of calculus. You can do optimization. So that's why we say optimal transport give you the foundation for deep learning. Okay. So here we can do a simple summarize. So given 2 points, okay, in the Wasserstein space, meaning give you two distributions, we can find the optimal transport map between them, which is governed by this motion pay equation. Okay, then if we know, okay, two distributions, we can define geodesic between those 2 points using Mercant displacement. So every point is a distribution. Okay, then we can define the remaining metric in this space using the polling method. So given 2 functions, then we can define their gradient vector field. And using density here, we can define their metric here. Okay. So in history, optimal transport was raised by Monge. So basically, given 2 distribution, how can you find a mapping, okay, from the space to from x to y, such that we push forward mu to nu, and among all such kind of mappings, we try to minimize the total transport cost. Okay, then this minimal transport cost is called Wasserstein distance. This gives you a distance definition between 2 distributions. Okay, then Conta-Roig, okay, relax the mapping to something called a transportation plane, which is a joint distribution. Okay, and make everything to be linear. Then he showed the existence, uniqueness for the solution. He got a Nobel Prize in economics in 1975. Okay. Then he also developed this duality principle. So then this figure is this formulation is very important. Okay. Then he introduced the concept for C transform. So by using C transform, there are only one unknown function here. Okay. And the functional become to this form. Basically, we try to calculate the expected value for Conta-Roig potential and the C transform expected value. Okay, so in deep learning field, if you read the paper, more than 95% is trying to optimize this functional, basically using a neural network, using different approximation, basically. But our method is very different. So basically, so if the transport cost is L2 norm, then Brunier developed this kind of Brunier theory. Basically, the OT map is given by convex function. Okay, the gradient of this convex potential give you the OT map. Then this Brunier potential U satisfy the classical motion pay equation, basically. So therefore, the most applications in deep learning boil down to solve this PDE in different ways, okay, using different approximation strategy, okay. Although there are a lot of fancy terms, a lot of fancy tricks, eventually they try to find an approximation to the solution to this one. And this one actually has a very strong geometric meaning, okay, so that's why we're using geometry to tackle the same problem, okay. So Professor Yao and Professor Sheng did a lot of work for high-dimensional Minkowski problem. So here is a simple case. Suppose we have a convex, okay, polyhedron embedded in R3. So if we know the normal to every face, if we know the area of each face, okay, they satisfy linear constraint, how can you determine the shape? So this is the problem. So you know that the area, you know the normal to every face, how can you determine the shape? Okay, the Minkowski prove the existence, uniqueness for the solution for lower dimensional case, and Professor Yao and Professor Sheng generalized to higher dimension and prove the regularity, basically, so that the theory holds for arbitrary dimension, basically. Now later, Alexandrov changed the convex polyhedron to open convex polyhedron. So suppose we have open convex polyhedron, which is the upper envelope for many, many planes. So if we know the normal to the supporting plane, and we know the projection area, so every face projects to the 2D plane, we get a cell. We know the cell area. Then there are some infinite, okay, cell here. So therefore, we define omega on the 2D plane. We know the intersection between the projection and this omega. We know the area, partial area here. So given such kind of data, we can determine the shape for this convex polyhedron. Okay, so if you write down the PDE for this problem, basically you get the same PDE for linear. Okay, so this is a motion pair equation from statistics, from probability, but it also has a deep roots in convex geometry. So therefore, in 1950s, Alexandrov proved the existence, uniqueness of the solution. Unfortunately, his proof is based on algebraic topology, so which is not constructive. So from his proof, you cannot develop a computational method. So therefore, more than 10 years ago, Professor Yao led us to give a variation approach to reprove the same problem. Basically, we found a convex energy. By optimizing this energy, we can find the solution to the Alexandrov problem. And this is the foundation for our AI work, basically. So here, we can show one simple example. Suppose you have a surface, this Buddha-Han surface. You're using Riemann mapping, you map it to the 2D plane. So this mapping will push forward the area element from surface to the 2D plane. So therefore, the disk has a measure, okay? We treat it as a source measure. But the disk has the bigger measure. Now, how can you find the optimal transport map between them? Okay, so this is the map, okay? So then you see, then this mapping, okay, to the original surface is an area preserving. Basically, you draw arbitrary region on the 2D disk. So the area here equal to the area for the region on the original 3D surface, okay? And then this mapping is given by the gradient for convex linear potential, okay? We see, okay, amazingly, the inverse mapping is also optimal. So therefore, the inverse mapping is also the gradient for this kind of mapping, for this function. And these two convex functions, they differ by C transport or around the due. So therefore, everything is very symmetric, okay? Then finding this function boil down to solve the motion pair equation, okay? But if we change from optimal transport to the worst transport, so basically, among all the possible solutions, can you find one with a maximum total cost? Same theoretic framework holds. So this is the worst transport map. And this is given by the concave function. The gradient of concave function gave you such kind of map, okay? Although nobody use worst map in AI, but in principle, you can either use an optimal transport or worst transport, same thing. So no difference, okay? Just people hasn't realized this kind of theoretic symmetry, okay? Okay, then how well does a deep learning system really learn? So does it really learn everything or have to forget something? So, okay. So we know that mode collapsing is the big bottleneck, right? We know it's really difficult to train a big model, right? So the model is really sensitive to hyperparameters. So sometimes the training process is highly unstable, right? And doesn't converge. So therefore, it costs a lot of graduate students time to do that. When you train one model, it takes months, right? Most time because you try to find the good hyperparameters. Yeah, even you have a big GPUs still. Then if you have several modes, in general, you cannot get all the modes covered. So you only cover part of them. Yeah. Then we try to understand why this happened. Okay. So here we can see some real example. So suppose we're using a MNIST data set, then we're using VE to generate such kind of data. Then you see a lot of symbols. Okay. Basically, it's not readable by human being. Okay. So this kind of phenomena is called a mode mixture or mode collapsing. Okay. So if you try to generate a human face, you get these kind of ghost faces. Okay. So this caused by the same problem. And this can be explained using a regularity theory from motion pay equation. Okay. So in the literature, there are a lot of mathematicians. They established the regularity theory for optimal transport. Okay, many existing results. Okay. So basically, given the shape for the source measure and the shape for the target spot of the measure, give you the regularity for the density function, we can predict the regularity for the mapping. Okay, but all the existing work, they assume the target domain is convex. Okay, so if you read all the literature, you'll see all the existing theorem assume the target domain is convex. So if the support for the target measure is concave, you get a lot of trouble. You get a singularity. Then Figali gave the following example. So suppose we have a planar disk. We have a uniform distribution, the density equal to 1. Then we have a concave shape here. Okay, so the distribution is also uniform. We calculate the OT map, optimal transport map. Then this map is not continuous. Okay, so then on the domain, you have this kind of graph. Okay, so here, if we approach this edge from the top, okay, then the image will approach to this boundary. So if we approach, okay, from bottom, so the image will approach to this boundary. When we cross this edge, the image will jump. Okay, and this phenomenon is pretty common. Okay, so using our geometry method, we can calculate the Brunner potential. So then you see that that's the Brunner potential, which is continuous everywhere, but not C1, not differentiable. So along special curves, special graph, okay, the function is only continuous, but not differentiable. So the gradient is not well defined. So therefore, this gives you the singularity set. So the existence of a singularity set, meaning the OT map is not continuous. But we know a deep neural network can only represent continuous map. So there's a big conflict there, right? We try to learn something we cannot represent. Then the whole process cannot converge or converge to the wrong answer, right? Okay, so here we show a high dimension case. We have a solid bunny, then we have a uniform distribution inside. We have a solid ball, we have a uniform distribution inside. And the mapping, we calculate the OT map. So then you see the surface of the bunny has a lot of foldings. So when you cross the folding, the mapping is discontinuous. So the folding gives the singularity. Okay, but all the existing work in AI, they ignore this issue. They assume that the OT map is continuous. Then they're using something diffusion model. Whenever you use a diffuse model, you smooth out all the boundary. You blur all the boundary. You lose the boundary information. And those information is critical. Okay, we will go there. So therefore, we get an infinite conflict. So neural networks can only represent continuous functions, but the OT map, they are discontinuous. Okay, so therefore, the whole training process cannot converge. Okay, so here you can visualize. We have MNIST. Okay, then we have the clustered structure here. We found an OT map between this square to here. Then you see along the cell boundary, the mapping is discontinuous. Okay. So then we try to validate our hypothesis by conducting the following physical experiment. So we're using human facial photo to train this data manifold. Okay, then we map the data manifold to the 2D plane, to the latent space. Okay, then in latent space, we have uniform distribution. We find the OT map here. So then we draw line segment randomly. So every line segment will be mapped to a curve in the latent space. Then by decoder, we map to a curve on the data manifold. So each curve actually is a morphing sequence from one image to another image. So here we can visualize some curves. So here you see we have small windows. So each window is a curve on the data manifold. Okay, then we can see the facial photos. Okay, transition is really smooth, very natural. So we have no knowledge about a human facial biology, right? Anatomical structure. Everything is based on statistics. Then you can get this kind of generative model. So we never know whether such kind of person exists or they will exist in the future, but it looks really realistic. Okay. Okay. Then our hope is that, okay. So we try to verify whether exists singularity. So if there's some singularity, we have some chance to cross the singularity. So if we cross the singularity, so that means the curve will cross the boundary of the data manifold. So therefore, you will get a curve cross the boundary for human facial photo manifold. So that means, what's the meaning for the boundary for human face? Okay, we consider all the human face form a special manifold. Now, what's the meaning for the boundary of this manifold? Okay, we didn't know the meaning until we conduct this experiment. So basically, by mathematics, that means there is some kind of face. Okay, they do exist, and they satisfy all the biological laws. But in reality, you encounter such kind of person, the probability is 0, right? Yeah. Then we really found such kind of example. Okay. So here is the first one we found. If we start with a boy, okay, brown eyes, brown hair, we end with a blonde, right? Then in the middle, if you pay attention, you'll see we have a sequence face. So one eye is blue and one eye is brown. Okay, so such kind of person do exist, right? Does exist, but the chance for us to encounter such kind of person is 0, basically. So if we really see all the training data set, so all the training data set, basically all eyes are either blue, okay, or either brown. But then this model gives you something new, something one eye is blue, something one eye is brown. So this means that the boundary of the manifold is really meaningful. Okay, so this verify, okay, the singularity really exists. Okay, the mapping is really discontinuous. Okay. Okay. But then what does this mean? So maybe we can analyze Sora. So we know Sora is extremely popular, but made a lot of mistakes. So we try to analyze the mistake made by Sora. Okay, so this is the first one, right? So you see, this one looks really realistic, right? But when she blow the candle, so the flare doesn't change. Okay, so what does this mean? Okay, so we know that for deep learning, for generative AI, everything is based on correlation. Okay, but here it's not a correlation; it's a causality, right? It's a physical law. So basically, physical law is extremely strong than correlation. You're using probability distribution to represent physical law is too weak. So therefore, AI currently can learn very subtle, okay, probability distributions, but cannot understand the physical law. So for strong causality, so AI hasn't reached there yet. Okay, so that's the point. Okay, so therefore everything is based on statistics. Then the statistics is too weak to represent natural laws. So so here we show correlation. So here everything is correlated with everything, right? But this is a causality. So you have reason, you have result. You have reason, you have result. So this is physics. Okay, this is the real world. But this is current AI. So therefore, how can we incorporate okay, causality to the AI model is the next big task. Okay. So here we just skip that. So here, basically, we know if using optimal transport, we have this joint distribution. So basically, this gives you many x caused by many y. So this is a correlation. But using a motion pay, basically every x corresponds to one y. This is a causality. This is much stronger than this one. Okay. But then, so there's another paradox. Okay, let me show that. So this one. So you see some paradox happens, right? Okay. So then why this happened? And here we have another example to show the same reason. Okay, this one. Okay. So all the videos are generated by Sora, right? Then they made the same mistake. So this mistake can be explained using the following figure, right? This very famous one. Okay, impossible stairs, right? So basically, we see the video is a local coherent, but globally is absurd, right? So because Sora, they use a token to generate everything, then they calculate the correlation among the tokens. So therefore, locally, everything is sensible, satisfy the nature law, right? But the AI has no global view. So globally, they made a big mistake, okay? Like the one shown here. So this is a geometric or physical locality and global, but this one actually comes from biology. Okay, so you see everything looks really realistic, except that the ant has only 4 legs, right? Yeah, but AI has no knowledge for the whole background, right? But locally, everything looks really sensible because AI only learn, okay, they chop the whole image to many blocks. So then they learn the probability among all the blocks, but it has no global view. Then how can we incorporate the global view to the current AI system? Like how can we introduce some kind of cohomology to the genetic model? That would be another task. Okay, but then we comes to this one, to this one. So this one is a very famous one, right? Okay, this one. Okay, and this one actually is similar to the following one from our point of view. This one. So you see the number of puppies change all the time, right? Why? Because in real physical world, all the physical process has a 2 state. One is called steady state, one is called critical state. Okay, so then so there are 3 puppy play that's the steady state, but due to the occlusion, okay, the number of puppy change, that's the critical state. So it's very easy to capture the images from steady state, but then very easy to ignore the critical state. But for human perception, the critical state is very important. Okay, so using our language, basically, you treat every image of 3 puppy as one point. Okay, then all the 3 puppy images form one cluster. All the 4 puppies, they form another cluster. Okay, but due to self-occlusion, sometimes 4 puppies become 3 puppies. So that happens on the boundary of the full puppy manifold. Okay, if we ignore the boundary information, we made a lot of mistake, physical mistake, right? But then how can we detect the boundary? So the boundary corresponding to the singularity of OT, right? So we come back here. Okay. So this shows that this boundary has a real physical meaning. Okay. So whenever we encounter the boundary, we shouldn't easily cross. We should see the real physical meaning. So if this set is 3 puppy, this set is a 4 puppy, we shouldn't cross, right? But for AI, currently people using diffusion, so therefore the boundary is blurred, and nobody knows the exact position for the boundary, and there's no physical law to prevent them to cross the boundary. So that's caused a lot of trouble for Sora. Okay. Okay, so then we propose our model. Basically, we see the central task for deep learning has 2, right? One is learn the manifold structure, finding the encoder decoder. So this can be carried out using conventional deep learning method. The second one is learn the probability distribution. So this one equivalent to solve a optimal transport. Then there's many ways to do optimal transport, like single horn. The only one which preserve the boundary information, singularity, is a geometry-based method. It's our proposed method. So although our method is more complex, but it gives you a more complete information, which is crucial for generative model. So this part basically using geometry model to solve motion pair equation. So therefore, we can precisely detect the singularity, avoid mode collapse. So we call this model as an AEOT model. Then we do some experiment to compare with the existing method. So the whole framework is as following. So given training data set, either image or voice or text, or video, then we do encoder, we do decoder, we map everything to the latent space. Then we find the OT map between white noise, to data distribution by solving Brunner potential. Solving Brunner potential basically is current to find a convex shape. The gradient gives you the map. So this convex shape, can be carried out by convex optimization using geometry method. Then if this shape is smooth, then basically the mapping is continuous. So if the shape, some part, is not differentiable, so that means we encounter the boundary between the clusters. So basically, so then this boundary either has a physical meaning or has a more geometric meaning. We should pay much more attention, at that part. So here we can see some simple example. Suppose we have this kind of data distribution. So each orange dot means one support, one mode. So if we use conventional GAN, we see we can cover some of the mode, but we also miss some of the mode. So this is a mode collapsing. So if we use PEG-GAN, then we can cover all the mode, but also we generate a lot of fake examples, among all the nodes, which is the mode mixture. So using AEOT model, basically we can cover all the modes and very clean. There's no fake examples are generated. So then we can compare for MNIST. For MNIST, we see using a VE, we generate a lot of mode mixture character here. But using our model, we get a much better result. For human facial photo generation, so our method give you a better result here. So then we collaborated with Google. So Google has a Google cell phone. On the cell phone, they have this keyboard, soft keyboard. So currently, people try to input every word letter by letter. But then Google try to promote drawing the curve for the input. For example, if you input a brain, you start with a B, and draw a curve goes to R, and to A, to I, to N. So therefore, every word corresponds to a curve pattern. But then the bottleneck is Google couldn't collect too much data, so therefore they have a very, very small data set. So they asked us to generate much more training data set satisfying the same distribution law. So that's why we're using our AEOT model to generate that. Okay. So for the next generation Google cell phone, they will use this method. Okay, you will see that. Okay, so in summary, we can see that we can try to using geometry to understand the optimal transport. Then we can using that view to explain generative AI. We see that the training data set can be summarized as a manifold distribution. Basically, each data set can be treated as a point cloud. So the manifold dimension is low, but the embedding space dimension is high. But also for different mode, we have a different distribution. So therefore, the goal for deep learning, try to learn first manifold structure, the second the probability distribution. Okay, then optimal transport basically give you a remainder metric for the space for all the distributions, which lay down the foundation for variation for deep learning. Then using the regularity theory from motion pay equation, we can explain the mode collapsing, and we see that the boundary for the support or the distribution has a very strong physical meaning. So we should pay much attention to that. Okay. Okay. Then basically, we see the OT theory has a lot of symmetries there, and give you a lot of insight. Okay. Okay. So I think it's stop here. Thank you.
Thank you, Professor Gu. Excellent talk. Any questions?
I think that's a good talk summarizing some of the phenomena of the deep learning. May you go to the last page so that I can refer to something?
This page?
Yeah.
Okay.
So you say that the module per equation explains the model collapse, which explains the abnormal phenomena during the human state and the video. I'm wondering, is there any very specific mathematical theorem that really justify that those problems is caused by this kind of?
Oh, okay. Let me show you this video again. Okay, I think this video is very, very convincing, right? So this video was generated by Sora. So basically, you see the number of puppies change. Okay, sometimes from 3 to 4, from 4 to 5, something like that, right? So basically, we're collecting a lot of short videos as a training data set. The 3 puppies is one video, right? 4 puppies another video. But then if we have 4 puppies, then when they play together, sometimes there will be self-occlusion. So then looks like 3 puppies, right? But this is a critical phenomenon. This happens on the boundary or the data support. Yeah, then because Sora using diffusion model, so diffusion model will blur the boundary for the support. So therefore, when we generate the data, Sora doesn't know this is the boundary and cross the boundary. So when we cross the boundary, 3 puppies become 4 puppies. Okay, then the boundary corresponding to the singularity or the OT map, right? Yeah.
So in this way, you can also predict those phenomena when it will happen.
Right. Exactly. Using geometry OT map, you can find a singularity. From singularity, you find the boundary. From boundary, when we approach the boundary, we should pay attention. Okay.
And what kind of boundary it may happen? Could you predict it before training such a model to?
Okay. So basically, there are a lot of critical phenomena in physical process. So the critical phenomena corresponding to the boundary, to the data set boundary. Yeah, in general. Yeah.
Okay.
Yeah, like this self-occlusion. Okay. Then for the one model, you see there are 2 steady state. Okay. So this is the one steady state. It's in the interior of the cluster. So when they go this way, it's another steady state, right? But in the middle, there should be a moment. Okay, the liquid flow out, right? That's the critical phenomena. That is on the boundary. But then this one missing the boundary, so therefore you do not see such a process.
Yeah.
But although the probability for boundary is a 0, but for human perception is important. Yeah, basically.
So I mean, this is just an infer from the equations, or the equations directly shows those phenomena.
Right. Basically, I mean, the training data set captured the boundary. So that's the input. Then using our method, we can detect the boundary in the data set. Yeah, basically. But if everything is missing, because the critical event is very difficult to capture. So most data set is missing the boundary already. Yeah, that is one issue. Yeah, even the data set has the boundary. Using diffusion model, they blur the boundary. So that's another mistake. Yeah.
Okay, thank you very much.
Okay, no problem.
Thank you so much, Professor Gu.
Thank you.
We really learned a lot from your very comprehensive
Yeah,
understanding.
I'm flattered.
So we have a major concern usually to distinguish correlation and causality.
Right, exactly.
Applying deep learning.
Yeah.
Do you think you decompose this process into two key steps?
Right.
Manifold learning and the probability distribution estimation.
Right.
Do you think the first one is a key step for us to tell difference between correlation and causality?
Right.
Thank you.
Yeah. Actually, the current model, all the AI model are based on statistics, so that they model everything using probability distribution. Yeah, but we know for causality, it's much more precise using PDE to represent that. Yeah, then that's the missing part for the current AI. Yeah, if there's some physical law, everything is deterministic. Okay, then the probabilistic description is too weak. But now there's no scheme so far. Yeah, to differentiate such kind of phenomena. Yeah. Another thing is because in reality, so there are so many physical laws. Okay, they govern everything all the time. But for AI, they only know very specific data set and losing the big picture. Yeah, then how can you incorporate all the knowledge to some physical law and using that for current AI? That should be the next step. Yeah. I fully agree with you. Yeah.
Any other question? No? Okay, let's thank our speaker again.
Thank you.